All right, so chapter 6 is kind of a short little chapter about chemical equations and really balancing equations and how to balance them. And that's what we're going to talk about in this chapter here. So first off, how do we know really a chemical reaction has occurred? Come back, there we go. So oftentimes there's visual clues that we can see. So for example, color change can indicate perhaps a chemical reaction has taken place. If you do see some type of color change that has occurred, a solid being formed is definitely a reason why a chemical reaction takes place. Bubbles as well is usually an indication that some type of gas has been formed. Heat is also a sign of a chemical reaction occurred. So again, if you're holding, for example, a test tube and it feels warm to you, then obviously that reaction is giving off energy in an exothermic sort of process as your hand is picking up all that energy, and that's why it feels hot. And vice versa as well. If you happen to be holding onto a test tube and it feels cold to you, basically it's an endothermic reaction. It's sucking out all the heat and energy from your hand, which is why your hand feels cold at that particular point. Clearly something burst into a flame, like I think we might saw a couple of labs ago when we watched like the I think it was potassium and sodium in water, right? So that's obviously an indication of a reaction takes place. As we'll talk about, there's really three reasons why a reaction takes place, and really a reaction will take place for really the formation of a solid, which is oftentimes referred to as a precipitate, the formation of water, and electrons being transferred. These are really three reasons why a reaction actually takes place. So as we'll talk about in the next chapter, which kind of is a continuation of this about types of reactions, what we'll see is pretty much all reactions boil down to one of those three things happening, either a solid being formed, water being formed, or really there's some type of electrons being transferred. So pretty much every single reaction, one of those three things are basically happening. And that's really the basis for why a reaction is taking place. So here's obviously some indications of a reaction taking place. We obviously see bubbles, which again is usually an indication of a gas being formed. Colors being changed here. So very common, for example, when we do a titration, we'll see a color change indicating that a reaction has taken place and that we have reached what's referred to as a equivalence point of that reaction. We're actually going to do something similar to this one here. We're going to make a yellow solid like that. So that's a precipitate, which is a solid. Also a reminder, sometimes people think a precipitate has to be like a rock hard solid, and it doesn't. It's just, something that wasn't there before. So it could be cloudiness, it could be something floating around in the solution. It doesn't necessarily have to be like a solid that just drops to the bottom type of thing. So if the solution gets cloudy when you mix two solutions together, that's considered a precipitate. A lot of times if you have a precipitate like this, we will do something like centrifuging it, and I'll bring all the solid together onto the bottom, say, of the test tube or something like that, and really sort of compact it together. Here's our hydrogen gas from calcium reaction with water. And obviously that is also a chemical reaction when we light the Bunsen burner. It's basically a combustion reaction, creating a flame and obviously heat coming off of it. And then some zinc and hydrogen gas. So let's talk about how we represent a chemical reaction. And we represent a chemical reaction through a chemical equation. And a chemical reaction is a chemical change. If you remember, a chemical change is whatever we start with and whatever we end with are fundamentally different things. So something has changed. You can't get back kind of the original substances by any type of physical means. So for example, here, if we take some hydrogen gas, oxygen gas, we can make some water here. As we know, you can do a lot of physical things to water, but you cannot get the hydrogen gas and oxygen gas back. You could throw it in the freezer, it'll just become ice, which is still water. You could heat it up and it will just become steam, which is still water. So no physical way to go back to our hydrogen gas and oxygen gas, which means that this is a chemical change. The only way to go back is a another chemical change. You'd have to do another chemical change to kind of go back and break that back apart, which is a type of reaction that we'll talk about in a later chapter as well. So when we look at a equation, there's a couple of things that are important. We could say, for example, that molecular hydrogen, which is something that hydrogen gas is oftentimes called, reacts with molecular oxygen to yield or to form is what the arrow represents, or to produce some water in this particular case. It's really important when you kind of have equations or write equations that you start with the correct sort of formulas first. And we'll talk about this a little bit more in a bit, but when we have an equation, we always want to make sure that it is balanced and that you have the right formulas down. So definitely if you're given something in words, you want to sort of put everybody into formulas like you were doing nomenclature, and then you should worry about sort of the balancing part of it. So sometimes people want to do both of those things at the same time and they end up with the wrong formulas. Things never end up balancing. So it's really important, as we talk about balancing equations here, that you first start out with the right formulas and then think about the balancing, and not try to do both of those things together. Now, obviously, when we look at the above equation, there's a problem with it, and the problem with it is not balanced. And whenever you have a chemical equation, it should always be balanced. So if we look at this, on the left-hand side of the arrow here, we should have the same number of elements on the right-hand side of the arrow. And if we look over here on the left-hand side, which are known as our reactants, these are known as our products. On the reactant side and the product side here, for hydrogen, we have 2, and we have 2. Remember that the number here goes to the guy to the left. And for oxygen, we have 2. And we only have 1 here. And again, if there's nothing written, then it is assumed to just be 1. So this is an unbalanced equation, which you should never, ever use in anything that you're doing in chemistry. But sometimes you do come across unbalanced equations. And the law of conservation of mass tells us that we really should have the same number of elements on the starting and the ending side of the arrow. And that is because, as we've talked about with bonding, and what happens when we have a chemical reaction is simply all we do is break bonds. And when we break bonds and make bonds, the only thing involved are electrons. And the really important thing in terms of the atom as to what element it is protons, which are in the nucleus. So in a chemical reaction, we really don't touch anything in the nucleus. So the elements always stay the same. So if you started with 4 carbons on the left, you should end with 4 carbons on the right. They may be in different sort of molecules or compounds, but you should not lose any elements, because really it's only electrons that are involved here in a chemical reaction that's happening and breaking and making bonds. So definitely when we have an equation, really one of the first things that we want to look at is fixing that problem, and fixing it by balancing the equation. So anytime you see an equation, anytime you write an equation, after you have the equation, that should be really the first thing that you look at is the balance. So we could fix this very simply, and a really good way to balance equations or help yourself balance equations is to make sort of like a little table like this, and frankly just record what you got going on each side, as we just did in that previous slide. And it also helps you sort of figure out where you should go to try to balance. So clearly from my table here, I can see hydrogen is good on both sides, but I do see that the oxygen on the right-hand side is less than on the left-hand side. So when we go to balance it, it is only the coefficients that we change. So we would put a 2 in front of, say, the water here. When we change the coefficients and put a number in front of a formula, it goes for everybody behind it. So that guy gets distributed to everybody behind it on that side. And that means now we have 4 hydrogens and we now have 2 oxygens. And that's a very common thing that will happen. You will fix one thing and frankly screw up something else in the balancing process here. And that's okay, because if we look at our table, we can clearly see that all we have to do now is go to the hydrogen on the left and basically do the same thing. And we could put a 2 right about there. And now again, this 2 goes to everybody behind it. And that's going to give me 4 hydrogens and now 2 oxygens. And now I have a balanced equation. So oftentimes when you're going to balance equations, just making like an initial table sometimes can help you sort of figure out where to go, maybe where to start. That's a really good sort of method. If not, maybe at the end you should make a table just to verify that it is balanced. I've seen a lot of people like turn in equations going it's balanced and it's nowhere near being balanced. So that's also a really good idea to make a table at the end. Any questions on that? All right, so as you can see here, this is the balanced equation by putting those coefficients. And let's talk about some other parts of the equation here. As I mentioned before, everybody on the left-hand side of the arrow are our reactants. And our reactants are really the starting material here in a chemical reaction. And they're always on the left-hand side of the arrow. All right. Feel like he's trying to get that point across maybe back there. Not back. All right, so on the right-hand side of the arrow, there are products. And products are really what is formed as a result of the chemical reaction. And always on the right-hand side of the arrow. So always reactants to products when we have this equation written correctly. And again, always should use a balanced equation. So I would say in general, if you see an equation, there's some numbers there, probably going to be balanced, but you should take a look at it. I would definitely say if you see an equation, there's like no numbers written in front, no coefficients, you definitely should take a pretty good look at it to make sure that it is balanced or not balanced. But definitely if you see numbers, I would say probably 9 times out of 10, unless somebody's trying to trick you, it is probably a balanced equation. Here again, there's our reactants, potassium metal and water. The reaction of potassium with water here. And there's our fire. When we look at an equation that is balanced, there's different ways that we could look at those coefficients, which are going to be important in a later chapter. But really, we can look at the coefficient as molecules if they are molecules. So, and these numbers come from really just the coefficients in the balanced equation. So we could say 2 molecules of H2 react with 1 molecule of O2, gives us 2 molecules of H2O. We can also say 2 moles of H2 react with 1 mole of O2, gives us 2 moles of H2O. This relationship here is the basis of what's known as stoichiometry, which we'll talk about in a later chapter. And that is why the first step that you should always do is make sure that the equation is balanced, because if you do not and you continue on with a calculation, you will have the wrong calculation because your equation is not balanced. So it's really important to always do that. The last part is conservation of mass. We have about 36 grams of reactants, should yield us 36 grams of products, and that's because the hydrogen on the left and the oxygen on the right and left, they both have the same mass. Hydrogen is 1.008 grams, oxygen 16, so they weigh the same on both sides. And if you have equal amounts, obviously on each side, you should have the same molar mass, basically, of all those reactants and products together. There's other information that's commonly found in equations, and those are the states of equations, or states of substances. And that is our S for our solid, and it's usually written to the bottom right of a formula. L for liquid, G for gas, and as we'll see in the next slide there, AQ for aqueous. And these are very commonly, again, found next to the equations or the formulas in an equation to indicate what state they are in. Although we do use equations mainly for chemical changes or chemical processes or reactions that take place, we also do use chemical equations for any type of physical process that's happening as well. So that's what we see down here. This is water going from the liquid state to the solid state. That's basically water freezing, right? So it's basically freezing. It's really water on both sides, but again, it's more of a physical process, but we can use a chemical equation to represent a physical process that's happening. Are the same thing here. This is basically water boiling, right? Going from the liquid state to water in the gas state. And that would be the process there of boiling. So again, the states are really important, especially if you're doing some type of equation for a physical process. Otherwise, we would just have water on both sides and not really have an understanding of what's happening, right? So a lot of times those states are important to put in there, especially if you know them, and especially if you're doing some type of physical process where you could have the same sort of formula on both sides of the equation, but it's the state that will tell you sort of what is happening in terms of the process. Other things that sometimes you will see is maybe you will see water written above the arrow, and that usually indicates that something's being dissolved in water. So that's very commonly done. So for example, here, if we take some solid sodium chloride, we will get sodium chloride that is aqueous. Once again, here is the same thing on both sides of the equation. This is also a physical process, but it is the different states here that tell us what is happening. We're basically dissolving that and making a solution. And that's pretty much what aqueous is a water environment. It's pretty much a solution. So all those solutions that we use in lab, they're just out of those bottles that drop. Those are all aqueous solutions. They're all basically a water-based solution in most cases. Now, there is a difference between the state of liquid and something that is aqueous. And just to explain the difference between these things, something that is a liquid is a pure substance by itself. So if you had water by itself, that is a pure substance. And that would have a liquid or L sort of signal to it. If you took water, which is a pure substance, and you added some solid sodium chloride, like the equation on the bottom, these two things, the sodium chloride will dissolve in the water, and that will make a sodium chloride solution, which gets the aqueous. So again, these are typically solutions. These are typically pure substances that are liquid. So they're both in the liquid state, but there is a difference as to sort of how you get them there. One just kind of is a liquid, and one is really a homogeneous mixture. A solution is a homogeneous mixture. So it actually is a same thing. Yeah. And that's what this is, right? So if we went back to just our mixture sort of conversation we had in that chapter, this is basically a homogeneous mixture, right? It's salt water, right? And that's basically what a solution is. That's actually the definition of a solution, is a homogeneous mixture of basically two things: something that is a smaller part, which in this case would be like the sodium chloride, the stuff that gets dissolved, and something that's the larger part, which is the solvent, like the water in this case. Yeah. Other questions? Okay. Other things that we sometimes will also see, speaking of the arrow, is sometimes above the arrow, things that are catalysts will be written. And a catalyst is not a reactant. It's not a product. And it does not get used up. It is there really in most cases to make the reaction occur faster. It basically can speed up a chemical reaction. It does so, and I think we talked about when we were doing the energy chapter, it finds really an alternative pathway for that reaction to take place, a more efficient pathway, and it lowers that activation energy, which allows the reaction to occur a lot faster. So sometimes on arrows, you'll see things written like metals, like PT. You may even see H+ written, which is a acid catalyst. So a lot of times, very commonly in equations up on top of the arrow, they'll kind of list whatever thing maybe is used as a catalyst, and again, is not considered a reactant or a product and doesn't get used up in that reaction. Is there just simply, let's say we've talked about, I think in that energy chapter, just to facilitate that reaction occurring a lot quicker. Any questions on any of that there? All right, so let's talk about balancing equations and some steps and some other steps. But the very first thing is, and you may come across this a lot, is again, you may be given sort of the equation in words, and you need to turn those words into the proper chemical formulas first. As I was mentioning earlier, you definitely want to make sure that you're starting with the correct formulas. because if you are not, the balancing part's going to be a really long day. Yeah. So if you got to first get that thing into the right formulas, and then you should do the balancing. That goes with if you're given something that is all words and you need to turn them into formulas. That also goes for, it's very common as well. You'll come across a lot of times, you'll be given like this side of the arrow, the formulas, and nothing on the other side. So you have to kind of come up with the sort of equations and formula. And a very common, like I said earlier, people try to do both of those things together. They try to balance and write the formulas, and they usually end up with the wrong formula and cannot balance it. So always do it in this order, as I've been mentioning. Correct formulas first, then balancing part. Never mix them together. Never worry about the balancing until you have the right formulas. Once you have that, that is the unbalanced equation. Remember that when we balance an equation, as I mentioned earlier, it is only the coefficients that you can change. So like we did with the water, we could only put a number in front when you do it. Why should I never change any of the subscripts? What happens if I change the subscripts? They're no longer like water in this example, right? So you can't change the subscripts ever when you balance the equation. Otherwise, you change what it is. You can also not do other weird things that people do, like put a big number in between things, like, you know, H2, I need like a 3 here, like that. You know, you can't do any of that craziness as well. That also screws up the formula. So only the numbers in front is the only things that you can change. You could start with the most complicated one first. You could also start with, in my opinion, what seems the easiest to sort of balance is sort of like the best idea. Make a table and go, okay, this guy could just put like a 2 there. We're good to go on that one. And everything else will sort of fall into place. When you are done, you're basically going to put some coefficients, one side, both sides at once. At some point, you should end up with a balanced equation where you have the same number of elements on both sides, and you should check that. When you have successfully balanced the equation, there's really 2 things that need to happen. The first thing is it needs to all be whole numbers for the coefficients. So all these things here have to be whole numbers, and they have to actually be the simplest set of whole numbers. So it's got to be the simplest set. And what I mean by that is, in my example that I just wrote, can I reduce those numbers down by a number? I could basically divide them all by 2 and still hit whole numbers, right? So technically speaking, this would not be the right balanced equation, although they are all whole numbers. They are not the simplest set of whole numbers. I would need to go through and divide everybody by 2. And this would be the properly balanced equation. Now, this happens a lot because some people could see larger numbers to balance them, right? Some people maybe see the smaller numbers. So what you want to do is check those 2 things when you're done balancing an equation. Once again, all whole numbers, and they need to be the simplest set of whole numbers. So if you could find yourself able to reduce those coefficients down by a common number and still have a whole number, you should do that, and that should be the properly balanced equation. Any questions on that there? Here's another approach. Again, you can use suitable coefficients, look for ones that appear only once on each side of the equation in equal numbers. Formulas that have these elements you can do with the same coefficients. So, you know, my personal thing is most people do a trial by error type of thing, but the best thing to do is to make a table, see what is the simplest thing to work with if it's only in one sort of formula on each side. So let's take a look at one together here just to kind of see the approaches here. Here's the rest of that second approach in case you'd like it. All right, so let's take a look at this one. So if I was to balance this equation here, the first thing really I would do is rewrite it because I don't have a lot of room. You might not need to do that, but we'll do that here. The first thing that I really would do is make a table. So I'm going to have the reactant side, I have a product side. I'm just going to list my elements here: nitrogen, oxygen, hydrogen. And again, I'm just going to take an accounting of what we got going on each side of the arrow. Left-hand side, we have 1 nitrogen, which is right here. Right-hand side, we have 2 nitrogens, which is right there based on that 2. Left-hand side, we have 1 oxygen there. Right-hand side, we have 1 oxygen there. Left-hand side, we got two hydrogens. And right-hand side, we have 2 hydrogens. First off, any questions on how I got those numbers there? So by making the table, again, it really does help you sort of or maybe organize in your head as to, what seems like a good place to start with. So in this case, from my table, I can see pretty much everything is balanced except for the nitrogen. So clearly that's a good place to start. And our nitrogen on the left there needs a little help. So once again, we're going to put the appropriate coefficient there on the left, which is a 2 in this case. Once again, when we put the 2 there, it does go for everybody that is behind it. That means here we do have 2 nitrogens. We now have 2 oxygens, and we still have 2 for our hydrogens. So much like I mentioned a second ago, we do see that usually when you put a number down, it will kind of fix one thing, but probably mess up something else. So this is where the table could also help us. We obviously clearly fixed the nitrogen, but kind of screwed up the oxygen. So that seems like a really good place to go next. And again, it just sort of helps you go to where you need to. So to fix the oxygen on the right, I'm going to also have to put a 2 there in front of it. And when I put a 2 in front of it, it again goes to everybody behind it. So that means here I still have 2 nitrogens. Oxygens, I now have 2. And hydrogens, I have 2 times 2, which is 4. Once again, looking back at our table, we can see the last thing here that we need to fix is the hydrogen on the left, which will also need a 2 in this case. And once again, going over there. So that's going to give us 2 nitrogens. That will give us 2 oxygens and 4 hydrogens. And now we have a balanced equation at this point. Any questions on that? So again, here I didn't change any of the subscripts, only the coefficients, and that's definitely all that you want to change. Any questions on that one there? All right, so why don't you try one here? All right, balance this guy up, see what you get him up with here. Okay, so let's take a look. So once again here, I'm going to make a little table, reactant product side. We got carbon, hydrogen, and oxygen. On the left-hand side there, we have 3 carbons. Right-hand side, we have 1. Left-hand side, we got 8 hydrogens. Right-hand side, we have 2. Left-hand side, we have 2 oxygens. And on the right-hand side, how many oxygens do we have? We have 3. We have 2 there plus 1 more over there. So that's going to be 3 oxygens in this case. At this point, not much is solved for. So really, probably carbon is going to be probably the easiest to start with since we have 3 on one side and 1 on the other. So we could put a 3 in front of the carbon. That again is going to be distributed over here to the back end. That's going to give us 3 carbon. Our hydrogen is still 2. Oxygen, we now have 6 off of here and 1 more over here, which looks like 7 in terms of oxygen at this point. Now, really the next easiest thing to fix is hydrogen. Why do I not want to go with oxygen at this point? Oxygen's in a lot of places on the right and 1 place on the left, and so there's a lot more sort of things tied to it. Hydrogen's really just by itself on the right, which makes it pretty easy to fix. So that is where I want to go next. So I'm going to go with a 4 there to get me to the correct number. And again, this is going to get distributed to everybody behind it. And that's going to give me still 3 carbons. 4 times 2 is 8 hydrogens. Now in terms of the oxygen, I still got 6 here. And now I have 4 over here, which gives me 10 at this point. Now that I locked everybody on the right-hand side, I clearly don't want to touch any of those numbers. So the much easy move now is just to go to the left and fix our oxygen, which is all by itself over there. And we could fix it by putting a 5 right about there. That gives us 3, gives us 8, and 5 times 2 is 10 in this case. Yeah. Any questions on that there? So sometimes it's best to leave that one that's in multiple things for the end, and especially if it's in multiple places on one side, that element, and like it's sort of elemental form by itself on the other side, like a diatomic molecule. It's a really good idea to kind of leave it to the end. Any questions on that there? All right, take a look at this one here. Write the balanced equation for this here. Diboron trioxide reacts with water to form boric acid. So see what you come up with here. Okay, so let's take a look. So once again, if you happen to have this in words like we do, here's what we were talking about earlier. We want to get the right formulas before we think about the balancing part. So diboron trioxide is a type 3 compound, so that's a B2O3. Obviously, water here is H2O. So before we begin, we want to not even worry about the balancing part. We want to make sure we get the correct formulas down. Now that we have the correct formulas, now we could worry about the balancing part here. Right, a little bit more room here. And once again, we'll make a little table. Reactant, product side, boron and oxygen, hydrogen. Left-hand side, we got 2 borons. Right-hand side, we have 1. Left-hand side, we have 3 plus 1 more gives me 4 oxygens. So 3 there and 1 there. Now, in terms of this 3, it does get distributed to everybody inside the parentheses here. So that would give us 3 oxygens on the right. And on the left-hand side there, we have 2 hydrogens. And once again, distributing that in gives us 3. There's not much to work with here. So we're going to go with the boron, which is the easiest. So we're going to put a 2 in front. Now that we have a 2 in front, this also gets distributed to everybody behind it as well. So that gives us 2 borons. We have basically 3 times 1 for the oxygen times 2, which is 6. And 3 times 1 for the hydrogen and times 2 in the front, which also gives us 6. Any questions on that there? We got our boron, and we really can't do much with anything on the right-hand side. So once again, I'm going to go with what is the simplest on the left, and that's hydrogen. It's only in one spot on the left. Oxygen's in multiple spots, right? So that's a mess. So we're just going to go with the hydrogen here to start with. And in this case, we have 6 hydrogens on the right, 2 on the left. We're going to put a 3 here in front for our hydrogen. Going to give us 2. Going to give us, for our oxygen, 3 here. Also 3 here, which is 6, and 6 for the hydrogen. So in this case, by fixing the hydrogen, it also fixed the oxygen, which is also very common when you're balancing equations. When you fix one thing, it may also fix some other element as well. Any questions on that one there? Okay, so why don't you give it a try here, this one. Balance this one up here, a little NH3, O2, NO, and H2O. Okay, let's take a look at this one since we're getting to the end. We're going to take our same approach here. So we have our table. We got 1 nitrogen and 1 on the right. We got 3 hydrogens on the left, 2 on the right, and 2 oxygens. And again, 2, 1 here and 1 here is 2 oxygen. So in this case, everything's balanced except for hydrogen. And really the common number to get that balance is going to be 6. So we actually need to put a coefficient on both sides. So to get our hydrogen on the left to 6, we're going to put a 2. And to get our guy on the right to 6, we're going to put a 3. That then gives us 2 nitrogens, gives us 6 hydrogens, and 2 oxygens. On the right-hand side, we end up with still 1 nitrogen, 6 hydrogens, and we have 4 oxygens, as we have 1 there and now 3 there. Next easiest thing to perhaps fix, again, is nitrogen, as it is by itself really on each side. And to fix the nitrogen, we could put a 2 on the right. That's going to give us 2 nitrogens. We'll still have 6 hydrogens. And now for our oxygens, we have 2 here and 3 here. That is 5. So we clearly now have everything balanced except for the oxygen. We only have 1 more spot to go. We don't want to change any of the other coefficients, otherwise we just screwed up everything we just did. So we basically need to turn a 2 into a 5. And in this particular case, in order to do that, we could actually use a fraction to do that. And we could use something like 5/2, for example. And if I do that, that gives me 2 nitrogen, gives me 6 hydrogen. And what do you get when you take 5/2 times 2? You get 5, yeah, which is what we're looking for. So I have this equation. It is balanced, but is it correctly balanced at this point? It is not. So this is a good example. You can use a fraction to balance the equation, but you cannot leave the fraction. So we do have to clear the fraction here by multiplying everybody by the denominator, which is the 2. And that will give us 4NH3 plus 5O2 gives us 4NO plus 6H2O. And if I did everything correctly and didn't screw it up, I should still be balanced. That's 4 nitrogen on the left, 4 on the right. I got 12 hydrogen on the left. I have 12 hydrogen on the right. I got 10 oxygens on the left, and I got 4 oxygens here and 6 more here, which is 10. So you definitely could use a fraction. How do you pick the right fraction? It's pretty simple. Number on top is the number you need. Number on the bottom should match that number. So that's how you could choose the right fraction really quickly, just whatever number you needed. So if you look back on our table, we needed 5. So 5 up on top, 2 to match will give you the right fraction. Any questions on balancing equations there?